Hello, everyone. Okay, let's get started.
Hello, everyone.
Welcome to this processing in memory lecture. So today we are going to shift gears a little bit from previous lecture where we talk about processing near memory architectures, and we are going to talk about one of my favorite topics on processing memory, which is processing using memory architectures. And this is one of my favorite topics because it's actually where most of my PhD dissertation is heading towards. So several of the works that I'm going to talk related to processing using memory are works that I developed myself here in Safari. But before that, just some quick terminology again as a recap. So we are here in this class trying to solve this problem of data movement bottlenecks in current systems by developing what we call processing in-memory architectures, those architectures are what we call memory-centric architectures, where we do computation near where the data resides or where the data resides itself. And last week we talked about one realization of processing memory, which is processing near memory architectures. And in processing near memory architectures, we are going to take some logic, some processors, some fixed functional units, some reconfigurable logic, and we are going to place that logic near the memory array itself. So either in the logic layer of the stack chip, or near a DRAM bank, or near a DRAM subarray. So today we are going to talk about something else. We are going to talk about processing using memory architectures. And here we are using a different paradigm. So for processing using memory architectures, we are not going to add any logic for computation. We are going to just use the analog operating principles of the memory cells themselves to perform some sort of computation. We might add some logic in the peripherals to help or to accelerate the main computation, but the computation itself is going to be performed using the memory cells themselves. So this is quite a radical shift from the von Neumann architecture, where memory is treated as only memory and storage and logic is treated only as logic. Now memory is going to be both logic and storage. So we are going to start really quickly. So throughout these weeks, we are going to build on top of this process using memory substrates, adding complexity as we go. But we are going to start relatively simple. We are going to start with data manipulation operations inside the DRAM chip. We start with data copy and data initialization. So data copy and data initialization is important in many different applications, like forking in operating system, or page migration, or checkpointing, or zeroing, or virtual memory cloning. And there is this study from Google, from this paper in 2015, that shows that aggregate across all of the Google data centers, 5% of the execution cycles are expended on data copy and data initialization, so move and mem copy instructions. This number might not sound big at first sight, but you need to think about how many the sheer volume of compute that actually a Google data center has, right? So 5% aggregate across all of those processors is quite a large number. So how we actually perform those operations in today's system? So let's say that we want to copy one row inside the DRAM chip to another row inside a different location in the same DRAM chip. So the way that you perform this operation in current chips is by moving cache line by cache line through the memory channel down to the caches, then from the source row, then you move the cache line from the destination row. You do the copy in the CPU or in the caches, and then you write back the data. So this incurs a lot of latency because you need to move the data from the memory to the caches to the processor and via the memory channel. A high bandwidth utilization because you need to move the data across you need to move the data through the memory channel, which is a quite narrow burst interconnect. It creates cache pollution because the only operation that you're going to do is copy one cache line to another. So it's not necessarily a useful operation. And you have unweighted data movement because ideally you not need to move the data outside the memory chip itself. So to copy 4K bytes of data via a DMA engine, which is alleviates actually some of those bottlenecks because you don't move the data through the caches. Still, this takes around 1046 nanoseconds and consumes 3.6 microjoules. So what we actually want. So if I just want to tell my DRAM chip to copy source row to destination row without intervention of the CPU at all, right? Because the data is already there in the memory chip itself. There's no reason for me to have to move it outside the chip to place it back inside the chip. So if you do the operation like this, you're going to incur low latency because you don't move the data through the narrow bus, a memory bus, to the caches, and eventually to the CPU. Low band utilization, actually you don't consume any bandwidth because you're not moving data through the memory bus. No cache pollution because the data does not reach to the cache, and no unwanted data movement. And if you do the operation like that in memory, we can reduce the latency of these 4 kilobytes cache, 4 kilobytes real copies from 1046 nanoseconds to 90 nanoseconds, and the energy consumption from 3.6 microjoules to 0.04 microjoules. So it's much significantly cheaper in both in terms of performance and also in terms of energy efficiency. So for us to be able to do that, and in the following lectures where we're going to talk about processing using DRAM architectures, we need to understand really well how is the organization of the DRAM chip is, because we are going to use that organization and the operating principles to perform computation. So this is a really brief and short introduction on how a DRAM chip is organized and operates. So this is a DRAM model. So a DRAM model is composed of many DRAM chips, and each DRAM chip is composed of several DRAM banks, and each DRAM bank has many DRAM subarrays, which are 2D arrays of DRAM cells. So the 2D array of DRAM cells are horizontally connected via word line and vertically connected via a bit line. The bit lines are connected to an array of sense amplifiers called a row buffer, and a DRAM cell is composed of a storage capacitor and an access transistor, which stores data in as charge inside the DRAM chip. So the access transistor enables and disables the charge to flow from the DRAM cell to the bit line. So this is just another view of a DRAM chip. So it's the same idea as before. So here we have a DRAM chip connected to the memory channel. Inside the DRAM chip, we have some chip I/O logic and several banks, and there is an interconnect that connects the I/O logic to the bank itself. Inside the DRAM banks, we have several DRAM subarrays and some bank I/O, and inside the DRAM subarrays, we have row of DRAM cells and the local row buffer. So the DRAM cell operates using three main commands: activate, read and write, and a pre-charge command. To read the charge level stored in the storage capacitor, the memory controller issues an activate command, and prior to receive this activate command, the bit line is held under a reference voltage, which is usually half VDD. So first, once the DRAM array receives the activate command, the word line of the target row is asserted, and which connects the DRAM cells along the rows to the respective bit lines. Second, the storage capacitor shares charge with its corresponding bit line. And third, the sense amplifier is enabled. Fourth, the resulting bit line voltage shift is sensed and amplified by the bit line sense amplifiers. Once the sense amplifier finishes amplification, the row buffer will contain the value originally stored within the DRAM cells along the asserted word line. Also, the charging the storage capacitor is fully restored, and at the end of the activate operation, the DRAM array is ready to receive read and write requests from the memory controller. The memory controller then issues read and write commands to columns within the activated row, and to prepare the DRAM array for future access to the other DRAM rows, the memory controller issues a pre-charge command. So it works as follows. First, the capacitor is connected from the bit line by disabling the word line. Second, the bit line voltage is brought to its quiescent state. Now the DRAM array is ready to follow up access. Third, the sense amplifier is disabled. So by using these operating principles of how you access DRAM, especially this activate command, we are going to be able to do in-memory row copies. So how you do that? The key idea is quite simple, and it has been proposed by this paper from our group called RowClone. So instead of issuing activate and reads and precharge comments, as I mentioned before, we are going to activate one source row. Then we are going to follow up that activation with activation to a destination row that we want to copy the data of the source row to. And finally, we are going to precharge the DRAM subarray. So what happens then? So when you first activate the source row, the operation is exactly what I just mentioned in the background. This activation row, the cells of the DRAM cells in this activation row are going to be connected to the bit lines. Perturbation on the voltage level is going to be sensed by the amplifier, and the data is going to then be amplified and latched in the row buffer. So we are going to follow up this activation for the source row with another activation to a destination row B. So this activation to the destination row B connects the DRAM cells in that row to the local row buffer. So since the local row buffer previously latched the data from row A, and the driving strength of the local row buffer is stronger than the capacitance in the local bit line, we are going. This local row buffer is going to push the data that was latched within itself into the second activated row, so the destination row here. Hence, realizing this in DRAM row copy. So it's a really simple idea. And this idea is to basically issue two consecutive activates, one for the source row, another one for the destination row, so that we can copy the data without moving it outside the DRAM chip itself. So all of these incur negligible area costs because we're not adding any circuitry to perform this operation. So this is another view on how this operation is performed. We call this operation fast parallel mode, in contrast to another operation that I'm going to talk later, which is called pipeline serial mode. So this fast parallel mode operation, as I mentioned, works like by the first activation, as exactly as I mentioned. The data in the DRAM cell is sensed by the local amplifier and also stored inside the amplifier as some temporary data. Then by activating the second row, we connect this second row to the local bit line into the amplifier, which allow us to copy the data that was previously latched into the destination row. So this operation allows us to copy one source row to a destination row within the same DRAM subarray. So by doing so, we can do bulk data copy with reduced latency. Reduced latency by 11 times compared to that DMA-based transfer that I mentioned, and reduce energy consumption as well by 74 times because we're not moving data outside the DRAM chip. So we also save bandwidth because we're not moving data outside the DRAM chip, and requires very little change to the DRAM chip itself. So the main constraints of this fast parallel mode is that the location of the source and destination rows. So they need to be placed inside the same DRAM subarray. Also, the copy of the data is a limitation because you're copying the entire row at once. So if you want to just copy portions of the data, we need to use what I'm going to mention next, the pipeline serial mode. So this pipeline serial mode allows us to use the shared internal bus that connects the different DRAM banks to the chip I/O to move data from one source row in a DRAM bank to a source row in another subarray in a different DRAM bank inside the same DRAM chip. So by doing so, we can improve the latency of DRAM row copy by 1.9 times and also improve energy by 3.2 times. So just to summarize, if you want to copy data inside the same DRAM subarray at the bulk, at the entire DRAM row, you are going to use the fast parallel mode, which basically uses two back-to-back activations to that particular DRAM subarray. And if you want to copy data across different DRAM banks, you're going to use this pipeline serial mode. If you want to copy a data from one DRAM subarray to another DRAM subarray within the same DRAM bank, the way that you do in RowClone is by issuing back-to-back pipeline serial mode instructions. Later on, we are going to see how we can improve this particular design. So we can use this in-DRAM row copy to do book utilization of arbitrary data. So you just initialize one row with the data that you want. Then we can copy that data to this row to many other rows as needed. So you also can do zero initialization, which is quite a common operation in many kernels. And here we are going to reserve one row in each DRAM subarray with zeros. And then we can copy this row from this reserved row to a destination rows using the fast parallel mode, which improves performance, reduce latency, and also reduce energy consumption with negligible loss in capacity for the DRAM chip itself. So this is just a summary of how much these RowClone operations reduce latencies and also improve energy. So what is important to highlight here is that the fast parallel mode here is the operation that provides the larger reduction in latency and reduction in energy consumption, because we can just do this back-to-back activations to copy data at once. Then if you want to move data across the DRAM banks, you need to do in a pipeline fashion using read and write commands in the pipeline serial mode, and this provides lower in latency reduction compared to the inter-subarray operation, but it still improves compared to using the DMA engine to do so. And finally, we have this inter-subarray, which since we need to do this pipeline serial mode twice, the reduction in latency is not much. It's the same as doing the computation via the CPU. But since we are not moving the data outside the memory I/O or the memory chip, we still can provide some energy reduction compared to the CPU. And all of this incurs very low area cost to the die area of the CPU and the DRAM chip. So for us to enable these RowClone operations inside a system, we need to tackle several system integration challenges. For example, how does the software communicate the occurrence of those bulk data copy initializations to the hardware? How we can ensure cache coherence, and how can we maximize the use of fast parallel mode operations instead of using the pipeline serial mode, so that we can have the largest latency reduction and energy reduction, and how we can also handle data reuse after doing zero initialization. So we're going to briefly mention solutions to those problems. So the hardware software interface, so that the software communicates to the hardware these RowClone operations. We include two new operations in the CPU ISA, main copy and mem init, to trigger those RowClone operations. And the proper microarchitecture implementation checks if the instruction can be sped up by RowClone, and if so, export the instructions to the memory controller. So since RowClone modifies data in memory, we need to maintain data coherence of the caches, but this is similar to the DMA request. So since both source and destination requests are in memory, we can leverage the hardware support for DMA to maintain data coherence for the RowClone operations as well. So also, we want to maximize the use of fast parallel modes and minimize the usage of pipeline serial modes, and you can do that by making the operating system aware of the subarray boundaries, so that we can try to place data that is going to be copied later on inside a single DRAM subarray. So there are several primitives that are amenable for the use of fast parallel modes, including call upon writes and bulk zeroing, which are quite common operations on when you are spending forking threads or doing operating system initialization. So after you do zero initialization, there are two cases there are two phases when you do this operation. The first phase, the operation system zeroes out the page, and the second phase, the application is going to use the cache lines from this page. So RowClone avoids the misses that is generated in the phase one, but it might incur misses in phase two because the data is not going to be bring up to the caches. To solve this issue, we create a new instruction called RowClone zero insert, which inserts clean zero cache lines in the cache itself. So we implement RowClone simulation, and where we simulate the out of order multi-core configuration of and use a cycle-created DR3 DRAM simulator. So we use 6 applications that are really heavy on row copy and row initialization to evaluate RowClone. Those include system boot up, compilation, forking threads in fork bench, mem cache for database, MySQL also for database, and some shell scripts. So we provide these applications and to characterize their memory traffic, and we see that several big part of the memory traffic for those applications is spent on zeroing, and also for some applications, some big part of the execution time or the memory traffic is spent on copy. So when you compare the IPC improvements and the memory energy reduction for this application, we see significantly improvement compared to the baseline and significantly memory energy reduction as well. So we conclude that the improvement that we see correlates with the fraction of the memory traffic the application presents due to row copy and initialization. So we also do some multi-core system evaluation where we run those CPU copy initialization test applications together with some spec applications. So half of the cores run copy initialization intensive applications, and the remaining half runs spec applications. So again, we see some performance improvements with the increasing core count because the CPU can use the memory bandwidth that is saved doing row copy operations to serve requests to the spec workloads themselves. And similarly, we see some memory energy savings compared to the CPU ISA, to the CPU system, due to a reduction in the traffic in the bus. So if you are more interested on RowClone, I invite you to check our Micro 2013 paper. So we keep following up on RowClone, so we can, for example, do faster inter-subarray copy and data movement at a smaller or larger side than DRAM bank. And I'm going to mention those two works next. So to do this fast row copy inside the DRAM subarray, we propose this mechanism called LISA. So LISA is going to use this case observation that even though there is low connectivity in the DRAM, so the main problem that limits the pipeline serial mode in RowClone is the low connectivity inside the DRAM chip, which bottlenecks data movement. So if you want to move data inside the DRAM subarray, we have this really high connectivity, right? Because if you can just the data, the rows are shares those local bit lines. But if you want to move data outside the DRAM subarray, we need to go through this internal data bus, which is much narrower than the internal data bus inside the DRAM subarray. And we want to basically provide new substrates to enable high connectivity between adjacent subarrays. Now, the key idea here is quite simple. It's called LISA, low-cost interlinked subarrays for fast bulk data movement between the DRAM subarrays. So the key idea here is to create some data path, some interconnects that connects the adjacent DRAM subarrays using some isolation transistor. So this enables us to do fast bulk data copy. We can reduce the copy latency from 1.36 milliseconds to 0.14 milliseconds, so 9.2 times improvement compared to RowClone. And we can also enable some other implementations of other mechanisms like DRAM caching and fast precharging, which improves by implementing this. We can improve such mechanisms by 2.2 times and 0.6 times, and we are going to mention these in more details next. So the main observation that we are going to use to implement Lisa is that bit lines serve as a bus as wide as the DRAM rows inside a single DRAM subarray. So when you want to copy the data from one row to another, we can use this very wide bus to do so. However, bit lines between the DRAM subarrays are close, so they are physically placed close to each other, but they are not connected, so they are disconnected. So this is why we need to move the data through this narrow global data bus. So the idea here is then quite simple, is to create a bridge between these different DRAM subarrays inside the DRAM bank using isolation transistors or links. So by doing so, now we can have exactly the same wide bus that we have inside a single DRAM subarray across adjacent DRAM subarrays as well. So by enable this, we can move the entire row from one DRAM subarray to another, creating a direct path across neighboring DRAM subarrays. And this wide path provides us high bandwidth and low latency for these DRAM row copy operations. So to enable Lisa, we create a new DRAM instruction called row buffer movement, or RBM, which moves a row of data in an activated row buffer to a precharged one. So this is how it works. So first we activate one DRAM row, and this is going to latch the data in the local amplifiers of that given DRAM subarray. Then you issue a RBM instruction from one with the target DRAM subarray to another, and this is going to assert the isolation transistors and connect the local bit lines from the source subarray to the destination subarray. By doing this connection now, the amplifier is going to start, the charge sharing is going to start happening between the bit lines in this local amplifier and the bit lines in the precharged DRAM subarray. And by activating the destination, the row buffer in the destination subarray, we can sense this charge sharing that's happening, and we can amplify the voltage level to the data that was originally placed in the source DRAM subarray. So we can basically, with RBM, transfer an entire DRAM row between neighbor DRAM subarrays. So we can cascade those RBM instructions to move data across more DRAM subarrays. So it's just we need to trigger the correct isolation transistor as we go. And to do that, to validate that, we implement the circuitry for these RBM operations using SPICE. And then we saw that we can move 4 kilobytes of data in 8 nanoseconds, which provides us a throughput for DRAM row copy across DRAM subarrays of 500 gigabytes per second, which is 26 times larger throughput than the bus throughput for DDR for 2,400 devices. And the area that is occupied for this isolation transistor is quite low as well. So we have an area of 0.8%, the DRAM chip area overhead. So we can use these operations, as I mentioned, to implement several things. The first one is what we call rapid inter-subarray copying, or RISC. And the main idea here is to combine these RBM operations with those RowClone operations, that back-to-back activation that I mentioned. So here we are going to first activate the source row, which copies the data to the local amplifier. Then we are going to issue the RBM operation that connects the isolation transistors from the subarray 1 to the subarray 2. Then we activate the destination row in the subarray 2, which allow us to copy the data in the local amplifier of subarray 2 to the DRAM row of the destination DRAM row. So based on that, we can reduce row copy latency in RowClone. We don't need to use that double pipeline serial mode anymore. We can directly use back-to-back activations with RBM in the middle, and that allows us to reduce the latency by 9.2 times and reduce energy consumption by 48.1 times. So we evaluate this operation using RAMulator with some memory-intensive workloads and some workloads that also do row copy. So the comparison point here is a baseline CPU that copy data through the CPU, and RowClone using fast inter-subarray via bitlines or slow inter-subarray copy via the internal data bus. So this is a summary of the results. So comparison over the baseline, we see that RowClone degrades throughput evaluated here as weighted speed up, because we need to use that pipeline serial mode. But if you do that row copy using the RISC implementation, we can improve the system throughput and reduce energy as well. So the conclusion here is that the rapid inter-subarray copying using Lisa improves system throughput on top of RowClone. So we also implement two other techniques using this approach. The first one is we call variable latency DRAM, VLA. So the goal here is to reduce DRAM latency with low overhead by trade-off area and latency. So main idea here is that if you have really long bit lines inside the DRAM chip, you're going to have to your sensing latency is going to increase. So we can reduce the sensing latency by chopping the bit lines, so having narrow bit lines, which allow us to have a faster activation per charge time. But this comes to an area cost, because now you have to replicate the local amplifier and also the local row decoder design. So the key idea in VLA is to reduce the excess latency of hot data via a heterogeneous DRAM architecture by adding fast subarray as a cache in DRAM range. So here we are going to use this fast DRAM subarray, which has fewer DRAM rows as a cache where we can access with reduced activation latency, and you're going to try to place hot data in that DRAM cache itself. So, however, since this is a cache, we need now to move the data from this potential, at some point we need to move the code data from a slow subarray to the fast DRAM subarray if the data becomes hotter, or the other way around. So if the data becomes colder over time, we need to move that row from the fast subarray to the slow subarray. We can improve this technique by using Lisa, by caching rows rapidly and moving them using the isolation transistor from the fast and slow subarrays as needed. By doing that, we can reduce latency of hot data by 2.2 times with only 1.6 the area overhead. So this is just a summary of their evaluation results. As we can see here, we improve weighted the speed up of VLA with together with Lisa by 5%, and we improve cache hit ratio as well. So another thing that we can improve is pre-charge time. So the problem here is that the pre-charge time is limited by the strength of the pre-charge unit, and we can use this linked pre-charge which allows us to use multiple pre-charge units to reduce the time, to improve the strength of the overall pre-charging operation, and hence reduces time. So here we are going to basically activate two or enable two pre-charge. It's not necessary to, but you're going to activate the pre-charge engines in two DRAM subarrays concurrently, doing a pre-charge operation, and link those pre-charge units using those isolation transistors from Lisa. And this allows us to reduce the pre-charge latency by 2.6 times. Again, this is a summary of the evaluation results. And the conclusion here is that by doing so, we can improve performance for 50 quad-core workloads. So there are many more results in the paper. So we can combine application, single-core results, mean sensitivity analysis, quantitative comparison to other heterogeneous DRAM chips, and also detailed quantitative comparison to RowClone. For all of that, we invite you to check our paper. So finally, we get to the final piece of data movement that we're going to discuss today, which is FIGARO. So just I need to give a little bit more background on how DRAM is organized. So we already saw that the DRAM subarray has many DRAM rows. And what is important here is that all the DRAM the DRAM rows are connected to a local buffer. So what's important here is that all of the local buffers in a bank are connected to a shared global buffer. And the global buffer is connected to the local buffer using a set of global bit lines. And this global buffer has a smaller width than the local buffer. So a single column of the local bit line is selected using a column decoder to connect to the global buffer. So when you want to operate DRAM, you already saw the activate and the precharge comment. But what's important here is when you perform a read comment, basically what you're doing is changing the address in the column mux, so that we can select the column in the local buffer and move this column through the global buffer and eventually to the chip IO. And the same happens to the write operation. So we are going to use these instructions to move one column of data from one DRAM subarray to another DRAM subarray. And the first observation here is that all local buffers in a bank are connected to this single shared global buffer. The global buffer has a smaller width than the local buffer, and we can use this structure to move data within a DRAM columns of data inside a single DRAM bank in a fine-grained manner. So basically here the idea is that you are going to create a path between the data from the search DRAM row via the local buffers, the column selection logic, the global row buffer, down to the local buffer in the destination subarray, and eventually to the destination DRAM cell. So based on that, we propose FIGARO, which is a fine-grained in DRAM data relocation substrate. So by doing FIGARO, we can relocate data across subarrays within a DRAM bank at the column granularity within a DRAM chip, or at the column granularity across many DRAM chips in a DRAM RAM. So to do that, we implement a new DRAM command called reloc, which transfer data from one DRAM subarray to another DRAM subarray via the global row buffer. So how it works? So here we have one DRAM subarray, another DRAM subarray, the local row buffer, the column decoder, and the global row buffer. So first we activate the row in subarray A, which copies the data to the local row buffer. Then we issue this reloc operation with the source row that you want to allocate and the column address within that row, and the destination row that you want to store that column and which column you are going to place the data. So the reloc operation is going to first select the column in the source row that you want to relocate. In this case, here is column 3. Then you're going to move that column from that source DRAM row via the global local row buffer. Then we are going to select the target column. Here is one in the target DRAM subarray. And finally, you're going to activate the DRAM subarray. And basically here you're performing a RowClone operation. So by doing this activation, we copy the data in the destinational column. So similar observation as in RowClone apply here. The drive of the local row buffer is stronger than the drive of the local row buffer, which is larger than the drive of the capacitance of the local bit line. So this is why we can copy straight from this local row buffer to the global row buffer to the global row buffer to the local row buffer and to the DRAM cells themselves. So the key features of FIGARO are we have 4 main features. So the first one, we can do this fine-grained column-wise data relocation, which is distant in this as independent, and the latency similar to the latency of a read and write command. So all of this is we can do at low overhead because you only require some column address muxes, some row address muxes, and some row address latches per subarray, which incurs 0.3% DRAM chip overhead. The latency of the reloc operation is quite low as well. It's 63.5 nanoseconds because we only need to issue 2 activates, which actually can be overlap the latencies, and 1 reloc operation and 1 precharge. And it's quite low energy consumption as well because you're not moving the data outside the DRAM chip. So if you want more information on FIGARO, I invite you to check our paper. Another work that we designed to move data inside the DRAM chip is NOM, which is basically an connect the many DRAM banks together, but I'm not going to talk about it over here. I want to highlight one of our works called PiDRAM, which is a substrate, FPGA-based substrate, which enables, which provides some APIs that allows you to do these row copy operations easily from the application in a prototype, in FPGA-based prototype, which uses violated DRAM time parameters to implement RowClone operations. So I'm not going to get into details on PiDRAM here because we are going to talk about process using DRAM operations in commodity off-the-shelf DRAM chips. I just want to mention that by using PiDRAM, we can do this in DRAM row copy initializations in not only simulation, but actually in a real FPGA-based prototype, which can still improve throughput and quite significant. So PiDRAM is publicly available in our GitHub repository, and if you are interested on the work, we can wait for the lectures later on in this semester, or you can read the paper or see Atterberg's lecture on the subject. So this is what we had for today. Thank you so much for your attention. So we start really simple today with showing how we can do in-DRAM data manipulation using the operating principles of how the DRAM cells or how the DRAM operates itself using this back-to-back activations in RowClone, and how we can improve the communication path inside the DRAM subarray or a DRAM bag, so we can further improve the throughput of those in DRAM row copy operations. So we are going to start really easy. We start really easy with simple operations. Next week, you're going to get a little bit more complicated with in DRAM majority operations. So stay tuned for that. So thank you very much for your attention. Let me see if there is any question. I guess not. So thank you so much and see you next week. Bye-bye.